about rectilinear motion, that is motion in one dimension. And in this case, we use three types of graph. The first graph we use to analyze motion in one dimension is what we call the displacement time graph. Now, when we talk about motion in one dimension, like I said, we have three different types of graph. The first graph is called the displacement time graph. The second type is called the velocity time graph. So we said we have a displacement time graph. Now, the second is called the velocity time graph. And the third graph is called the acceleration time graph. Now, we are going to carefully analyze all these three types of graphs and study how they actually work, how they behave. Now, in analysis of the first one, which is the displacement time graph, let us quickly use a simple diagram to explain how displacement time graph varies from one point to another. Now, another name for displacement time graph is also called the position time graph. Now, many students will have asked that in our syllabus, I am not going to be talking with respect to what we call distance time graph because there is no much difference in talking about the distance time graph and as well as what displacement time graph. Now, like I said, we are going to be considering different positions of particles that are moving from one point to another. Now, to do that, let's quickly analyze the first one for the displacement time graph in this case. Now, let's say we have a particle that is moving along that direction in the XY plane, and we have a body. Let us analyze in this way for proper understanding of the movement. Now, this is the graph of a particle that is moving in the displacement time graph. Please note that I'm drawing the displacement time graph of a particle X moving at time t. Diagram not drawn to scale. Now from here we can take a particular position P when the particle starts moving, and we say that at that point P, the particle has covered a distance of, let's say, t at that particular point. Then the position of something will be around this place, which we call what? The position at this place, we call it x1. Let's call the time at this point to be what? T1. So we say, directly we say, when we are trying to look at the variation of the displacement time graph of a particle P, it is the same thing as saying when we try to calculate the slope, which can be calculated by looking or drawing a tangent at this particular point, which I'm still going to do. So the slope at P now can be equal to what? The change in what? The change in what? The position of the particle, which we call the x, by what? The rate of change by dt. And remember, we have also discussed in early classes that the rate of change of position with time is called the instantaneous velocity of P, which I will call Vp. Now, similarly, we can also analyze by looking at drawing a tangent to get the slope, which we have actually known by ds by dt from early classes. But if we try to analyze that very carefully, we can say at this point in time, when we try to draw the line of the tangent, trying to make something that is unique. Now, drawing a tangent line at that point, we can carefully say that the angle at which this particular line is making with the positive x-axis in this point, as you can see here, the particular angle it is making with the positive x-axis, let's say here it is making an angle of theta. So it's the slope, which we call the x by dt, which you can also write as tan theta. So also, or similarly, the particle is moving, the slope is increasing at this point of tangent. If we consider another position, or at, let's say, here now, the decreasing part of the graph, we call that position Q, for instance. And we also try to draw another tangent, the tangent line, to illustrate the motion of the body. As you can see, we can say like at this point now, if we bring in the tangent, just like what we have done at that point, trying to make sure everything is carefully drawn. So here, looking at the tangent at this one particular point, which I call position Q. Now, the tangent of this curve here, you can see, is decreasing. Let me increase here so that we can see carefully. I will say the angle it makes with this is what we call, well, let's call this one, this is theta, let's call this one theta dash. Now, the angle here, tan theta here is positive, but in this case, because it's a decreasing slope, and because of that, we say the angle at which it is going to make here is an obtuse angle, that is 180 minus theta. And if we do that from what we know here, the angle here is a 180 minus theta, which is a negative or a decreasing value. So what we just need to consider here is that the velocity at this place, which I call velocity at Q, is an obtuse angle, which we call tan theta dash, from what I've shown. It's an obtuse angle, and it's always going to be negative, what? Negative value. So my dear students, what I'm trying to say here is that one thing, as a particle is moving in a displacement time curve, we have to consider that the rate of change of the displacement at different positions of time can be calculated by looking at the slope of the curve, which will give us what we call instantaneous velocity of the particle. And the slope of the graph can also be calculated as a tangent line that is drawn, which can be in the increasing part and also as the decreasing part. Similarly, we can take a practical situation to analyze how what displacement time graph varies at different positions. Now we can say, let's take a practical analysis. Now, looking at practical analysis because of call for examination, for our JUPEP students in particular, we can consider a particle as taking a particle that is initially at rest, a quick one, then the particle accelerates, and after accelerating, the particle moves uniformly, which are what many of us might have learned in early classes. And after moving uniformly, it retards and finally come to rest. Now, we can as well analyze this by drawing out our curve to explain deep how this works. Now, in this case, we can carefully say at an instance, as you can see, now here, the body is moving initially. We said it is at rest. We consider the displacement time graph. Students should keep it in mind. Consider displacement time graph, and we're trying to look at the particle analysis. Initially, it is at rest. We take the initial position here as rest. The body is accelerating. When the body starts accelerating, the slope will increase from what we've said. Then, after it accelerates, it moves uniformly. At the point in which it moves uniformly, we draw a straight line. So the straight line will be uniform movement, which you see from this point, there will be a straight line. Excuse me, the straight line is not that straight. Let me make it a little bit straight. Then we have most like that for a straight line. Then later retards, it retards. That means the slope is decreasing and comes to rest. So this is the analysis we can give to that in practical analysis for graphs that explain how the displacement time graph actually moves. So we can say the particle starts from rest here at time t equals to 0, moves to a point here where it accelerates at time t1. After that, the particle moves uniformly to this point at time t2, and finally comes to rest at this point, which we call time t3. So this is the analysis we give to displacement time graph in physics, and which I believe we have all learned in early classes. Now, these are graphs we can also see. I'm talking about the experimental situation, a quick one, my dear student. Looking at experimental situation. For experimental situation, we can consider a very simple one, which many of us have actually learned during our WAEC and SSCE time. And for WAEC students, you can quickly learn this when we talk about experimental situation of a body. Now, looking at this in experiment sake, we can consider a body that is moving towards the positive x-axis. Quick one, my dear student, because of time. And we say we are actually considering a body that is moving towards the positive x-axis. Horizontal lines are positive. In this case, we can say the body is starting from rest. That is at the point at which time is equals to 0. It is now moving to a point. Let's say we consider this point at time t1 with a velocity of what? Of v. It starts from rest, moves with a velocity of v1. Then what happened to the body is that at this time what t1, at the same time the body is at rest here also, so it moves with velocity from rest, which I will call v1. Then when the body reach t1, the body come back to rest. Then at time t2, then what happened to the body after stopping at this point was that it now go back to initial position, which I will call at another velocity, which I will call velocity v2. Now, students need to understand this, that the body moves back to its initial position and reaches the initial position at time t3. And when you are to illustrate this with your graph in early classes, what you do, my dear students, is just to understand that you can also bring a displacement or position time graph to analyze the situation. And in that case, let us quickly also analyze it so that we can move to velocity time graph and acceleration time graph in quick time. Now, a quick one, we can say that analyzing this velocity time graph of this body, we can quickly say that the body, in this case, is starting from rest, as you can see at time t equals to 0. So when it starts from rest, we can analyze as the body, this is the rest. Please always keep that in mind. As the body starts from rest, I'm trying to draw a position time graph. If you like to say displacement time graph, if you like to say distance time graph, but I can actually differentiate between distance time graph and what displacement time graph. Having learned that distance is what scalar and displacement is vector. Now, a quick one, dear students, we are talking about position, that is x against time, which is t. Now, it is starting from rest. Then the body is now moving with a velocity of v1, which we say it is uniform velocity at an angle of what? Positive. You can see the slope is increasing, starting from rest, move to that particular point, t1. Now we say it moves like this. That is uniform movement. This diagram not to scale, permit my diagram, or for better understanding, maybe I should go for a good diagram for us to see carefully. Now, dear students, here in this course, the body is moving uniformly at time t equals to 0 to a point of time t equals to t1, as you all can see. Now, this is rest, moves at an angle of theta. Let's say the angle is theta at this point, which is increasing. The value of tan theta is increasing. You can see it's a displacement time graph or position time graph, whatever you want to call it. Now, this happens at the time of t1. I believe we've learned this in early classes. Now, when it was at t1, the body stopped and maintained that particular point or course from time t1. You can see that is why it is now moving uniformly. That is how we illustrate that in experimental situation. So now after that, it moves uniformly from time what? T1 to T2. That is why it is still at the same position as you can see here. So we say T1 to T2, the body moves uniformly. Then getting back to T2 here, the body now returns back to its initial position at T3. And at that point, we say the body is retarding and it will come back to rest. And you can see this is the point we call T3. And this is the way you analyze in early classes how you draw your velocity time graph. So now in this case, we have angle here is theta, is an increasing value. We say the x by dt is the what? Instantaneous velocity. So also another angle is being made here, which we call, remember, I said this angle is negative, which I call theta 1 dash. So which is always going to be negative. So here, tan theta in this one, tan theta 1 in this case, is instantaneous velocity, which we can call v1. And we also have tan theta 1 dash, which we also call what? Instantaneous velocity of particle at this or that other point. So please always keep it in mind that you can also classify these, and it depends on the nature of the question. Then you draw the diagram, then you use the formulas to analyze this. Then the next one, the quick one, will be the velocity time graph. Now about the velocity time graph, we can quickly analyze that just like the way we've analyzed our displacement or position time graph. Now, I said something before I move because of time. I said something that the only thing that differentiate displacement time graph from velocity or from distance time graph is that for your distance time graph, the body will never come down. It will also continue to, because the distance this body moves from this point, let's say we classify the distance here to be x, and it's also moving back at the same x. So you say x plus x, which is 2x. But in displacement, the position is taken to be x, x1 minus x2, which we analyzed this before when we talk about analysis of instantaneous velocity and instantaneous acceleration. Now, a quick one, my dear student, on the second one. About the second one, we talk about velocity time graph. It is just the graph that relates. Velocity time graph is just graph that relates velocity with respect to time, rate of change of velocity with time. So it's what we call velocity time graph. Now, as we have carefully analyzed the displacement or position time graph, we can carefully analyze the velocity time graph in a quick way for understanding sake too. The same thing holds for this. But one thing we have to keep in mind here is that we have velocity. We are drawing the graph of velocity in meters per second against time, which is in t. Now, as the body starts, we carefully look at a body that is moving along a curve as discussed in the other one too. So if you carefully analyze this, we say at this particular point, which is the increasing part of the curve, you can take we can carefully analyze this particular point on the graph, and we call this point as point X, for example. So we are looking at, excuse me, my dear student. I want us to have a good diagram to understand the practical analysis of all this. Now, if we consider that we have at this point here, at that point X, we can consider the time at which the body is moving at that point as time t. Now, if we look at the change here, like I've said, let me carefully draw the curve a little bit like that. So that one, I want to draw the tangents. Now, the rate of change at which we have the velocity is changing with respect to that, because the velocity time graph is given as a function of time, which we've analyzed before. So if we carefully analyze this the way we've analyzed the other one, we can say that the rate of change of velocity with time, which we call the v by dt, is the same thing as tan theta, but this time it is not instantaneous velocity, because velocity is changing with respect to time. It is called instantaneous acceleration, which I call acceleration is what instantaneous. Now, here we have to also understand something. It is not only drawing the tangent, which we are carefully going to draw now. Drawing the tangent line at that point, if we draw that, that is what we're definitely going to give us the angle at which this is making towards the positive x-axis. So if we carefully analyze that, can say by drawing the tangent line, diagram not drawn to scale. So we have that. We can say the angle at which this make theta is the tan theta, which is the slope. Please, tan theta is the slope. So if you ask a simple question, that the slope of velocity time graph is what? The slope of velocity time graph is simply what? The acceleration. We can also quickly look at the second part of the journey, that is the decreasing part of the curve, and also bring the tangent line as already discussed, and look carefully into the tangent line. As you can see here, we can see that another angle is being made here, which we call theta dash, which we said is a negative value of what? This acceleration at this point is negative, and at the point of theta 1 here, acceleration at this point is always going to be positive. So students should be careful when dealing with acceleration time graph. Another thing I quickly need to talk about is that when we try to find we consider different position of this curve. Let's say we are taking this part as the first area, and we are considered this other point. Then we try to shade under this curve, as you can see, because of time, my dear student. So now, if we try to find the area under the curve, that's another important thing you have to keep in mind. Area under curve. We can do that from our knowledge of integration, which we've learned before we start the physics course. We said the area of that curve, we are taking it at the point of this time I call T1 or T2, and the first one I call T1. So we can say if we integrate to get the area under the curve, we know we integrate from time T1 to what? To T2. So, and if we try to do what we are trying to what? We are doing but area under curve of velocity time graph. So we call it area under curve of VDT. And if we do that, the area under the curve of VDT is called displacement. So always keep that in mind so that when you have questions on this, that calculate the area under the curve of your velocity time graph, what you're going to have, my dear student, is going to be the displacement. The same analysis we gave to this is the same thing as the second one. And carefully, we can quickly go to the third one, which is also very, very important, but not in details, because in the later part of our syllabus or in our syllabus, we are going to carefully analyze what is needed. Now, talking about the third type of graph, which we call the acceleration time graph, carefully, we can also look into that. And now, if we are to consider the third type of graph, which is the velocity, the acceleration time graph. For the acceleration time graph, now we can also carefully look at a quick graph, a quick one, my dear student, because of time. Now, if we consider that, so we have this. So we have our acceleration time graph in this spot. So looking at this, now we can also look at the curve, just like what we've been doing since morning. We have this. Oh, excuse me. So we have acceleration time graph moving under the curve, as you can see. Now, in our syllabus, like I said, we are not going to be talking extensively acceleration time graph because it is not required. Now, the only thing that is important is that we can consider the area also from a position of, let's say, time t1 to a point of time t2, just considering any point. This is acceleration time graph. My dear students, we can keep that in mind. So here, in this case, when we look carefully at the shaded area from what we have, just like the previous one, which is what I need to talk about. Remember, we are talking about acceleration time graph. Now, the area of the curve of acceleration time graph from what we've discussed will now be the integration. Whenever you are looking for area under any curve, it is going to be integration of the whole world of the area. Now we have a T1 to T2. We are dealing with A dt, so you have a dt. Now, the area of this one, A dt, is called the net change in magnitude of what? In velocity. So what I'm trying to say, my dear students of the particle, is that our area under the curve of acceleration time graph is called velocity. So that is the only thing we talk about here, because in our syllabus, it is not required for us to study carefully how acceleration is changing with time. So guys, this is all from me for now. So see you guys soon in my future